All right, what we're going to look at right now is something called ion product constant. QSP is a symbol for it. It is set up the same way as KSP. The difference is that KSP represents the solubility product when we are at equilibrium, when the solution is saturated. And we use KSP in comparison to QSP to determine if a precipitate is going to form. So the comparison between the two will be able to tell us this. If I were you, I'd probably take this information here, I'd pause the video, and I'd jot this down into my notes. So if we have the second bullet point here, if QSP and KSP are the same, our solution is already at equilibrium, it is saturated, no precipitate is going to form. If QSP, the calculated value of QSP, is less than the given KSP value, the solution is still unsaturated, so more ions could dissolve, therefore no precipitate would form with either of these first two examples. If QSP is greater than KSP, that means that too many ions have been added into this solution. They are not able to dissolve at that temperature, and so a precipitate will form from the excess ions that are present. We're going to look at this quantitatively. So what's happening here is that we have a mixture of two salts. Those two salts are, barium chloride and sodium sulfate solution. And let's take a look at what would happen if we added these two together. Got ahead of myself there. Barium chloride and sodium sulfate solution would form sodium chloride and barium sulfate. So first of all, the substance that would potentially form a precipitate is going to be barium sulfate. Sodium chloride is formed of ions that are always soluble in water, and then that would be the balanced equation there. So what we want to do first is we want to figure out how many ions are present. What we need to do is we need to be able to calculate for barium sulfate. We need to know what the concentration of barium ions are and what the concentration of sulfate ions are, because we're going to plug that into a QSP expression. We have barium ion concentration times the sulfate ion concentration. We are going to compare that to the KSP of barium sulfate. So the KSP of barium sulfate, I'm just going to write that across the top. KSP of, this is barium sulfate. I looked this up earlier in our Zumdahl textbook. It's on page 761. And for this substance, I have 1.5 times 10 to the negative 9. All right, here's how we're going to do this. We know that there's 10 milliliters of a 0.1 molar solution of barium chloride. 10 milliliters, we had to convert that into liters, so it's 0.01 liters of a 0.1 molar solution. For sodium sulfate, we have 40 milliliters of a 0.025 molar solution. So again, convert that into liters, so 0.04 liters of a 0.025 molar solution. What I'm looking for is the number of moles, and moles is equal to the molarity times liters, so that's what I'm going to be doing for both barium chloride and sodium sulfate. So 0.01 times 0.1 gives me 0.001, and this is moles. In this case, it is of barium ions. Those are the ions that I'm thinking about as part of my precipitate. So we'll hold on to that information for a moment. Now I'm looking for the concentration of my sulfate ions, since I know that sodium ions and chloride ions are spectators. Again, taking molarity, 0.025 times volume, 0.04 liters, and I end up with 0.001 moles of sulfate ion. So there's just one sulfate in that sodium sulfate. There's just one barium in barium chloride. And so here's my number of moles. Now what I want to do is I want to be able to plug in to my KSP expression. So I'm going to take this information. I'm going to use it in my QSP. However, we need molarity values to plug into our QSP expression. So my barium number of moles is 0.001 moles. And ironically, sulfate is the same concentration, 0.001 moles. Now what we need to do is to figure out the new volume of the solution. So if you take a look at what we were told, it was 10 milliliters of barium chloride. It was 40 milliliters of sodium sulfate. So now my total volume of these two is 50 milliliters or 0.05 liters. 0.05 liters. So my new molarity of barium ions here, let's see, is 0.02 molar. And my new molarity of sulfate ions, if I do the calculation here, it's the same for both of them, which is a coincidence. So 0.02 molar for barium sulfate. So now I'm going to plug that into my QSP expression. And for QSP, what I will have is 4 times 10 to the 4. Or, excuse me, 4 times 10 to the negative 4. Now, the key here is that we are now going to compare QSP to KSP, and we need to make a decision. Which one of these is bigger? So, just as a reminder, KSP is 1.5 times 10 to the negative 9. QSP is 4 times 10 to the negative 4. So, clearly, Q is much, much larger than K, and when that happens, when Q is greater than K, there's too many ions present. So this means that a precipitate will form. All right, there's our first example. We're going to run through this whole process one more time with a new example problem before we're done here. So in this next example, what we see is that we have a mixture of calcium chloride and sodium fluoride. And we're going to walk through the same kind of process one more time so you can get the hang of it. So we want to start with a balanced equation. We have calcium chloride and sodium fluoride. It produces calcium fluoride and sodium chloride. Our potential candidate for a precipitate is calcium fluoride. And the KSP, KSP there, of calcium fluoride. I looked this up earlier. Let's see. It is 4 times 10 to the negative 11. So here's what we're going to do. Same kind of process. We're going to just look at what we're given. We have 50 milliliters of a 0.006 molar solution. So I'm going to convert milliliters into liters. So it's 0.05 liters of calcium chloride in a 0.06 or 006. Good thing I checked that. 0.006 molar solution. For sodium fluoride, it is 30 milliliters or 0.03 liters of a 0.04 molar solution. And so again, I need the number of moles, which is molarity times liters. So 0.05 times 0.006 gives me 3 times 10 to the negative 4 moles, and this is of calcium ions. So we don't care about calcium ions here, care about chloride really, because chloride ions are going to be spectators, so we're really focused on calcium, and that's part of our precipitate. Same process here. We're going to take 0.03 liters of sodium fluoride times the molarity of that original solution, and that gives us 0.0012 moles of fluoride ion. We aren't really looking at the sodium ion because that's a spectator. So here's what we know so far. We know that calcium fluoride is the one that we are thinking could be a precipitate. It's based on concentration. At this point, we know that the number of moles of calcium is 3 times 10 to the negative 4. The number of moles of fluoride present is 0.0012 moles. And what we need to do is to plug into a QSP expression where QSP is going to be equal to the molarity of calcium ions in this new mixture times the molarity of fluoride ions squared. Again, reminder, it's a 2 here, so we're going to square that there. And we are almost to molarity. So what we have to do first to find molarity is to divide by the number of liters. Now this solution we had, what was it? 50 milliliters plus 30 milliliters. It gives me a total of 80 milliliters. So 0.08 liters of solution. And my concentration, when I divide that out for calcium, it's 0.0038 molar calcium. And for fluoride, it is 0.015 moles per liter of fluoride. Now, I don't want you to worry about this. So why am I not taking this times 2 since the coefficient had a 2? So here's the thing. The fluoride comes from the sodium fluoride solution here. And my amount of fluoride ions, the only source of fluoride ion is sodium fluoride. So I don't double it just because there's a 2 present in the balanced equation for the dissociation. That's how it's going to react in a 1:2 ratio. So now I'm going to take these two values for my new molarities of QSP. I'm plugging them in to my expression. So 0.0038 times 0.015 squared is going to be my QSP value. I do that calculation, and I get 8.6 times 10 to the negative 7. I'm just going to double check that once. I did it earlier today, but just want to check my math. All right, and I think that's good. I think so. We might be off, in rounding, but really what I'm looking at is more so the magnitude. If we recall the KSP, I wrote at the top, KSP is 4 times 10 to the negative 11. So will a precipitate form? Again, the key here is to compare QSP, so 10 to the negative 7, to KSP, which is 10 to the negative 11, and QSP is much larger than KSP, so indeed a precipitate forms here. There's too many ions present, and that is it. So that's our last video for Chapter 16 on ion solubility equilibrium, and please bring all of your questions with you the next time we meet. Thank you.